Here's problem 75 from Chapter 27, OpenStax College Physics. What are the three smallest non-zero thicknesses of soapy water of index of refraction 1.33 on plexiglass if it appears green, constructively reflecting 520 nanometers light when illuminated perpendicularly by white light? So let's write down our knowns. We know that we have air on top of the water that's on top of the plexiglass. So index of refraction of air is 1, index of refraction of the soapy water is 1.33, and we're not told what the index of refraction of the plexiglass is, but we can look it up, and it's about 1.5. Then we know that light of wavelength 520 nanometers is reflected, and we are asked to find the three lowest thicknesses, L's, so that we have constructive interference so we can see the reflected light. So let's draw here the thin film. So on top of the thin film is air. Then the thin film is actually soapy water, so it has index of refraction 1.33. And that soapy water is sitting on plexiglass, which has an index of refraction of 1.5. Again, we weren't told this, but what's important here is that the 1.5 is greater than 1.33. So if we have light striking the top of the thin film, that light will reflect and it will refract. So we know that due to reflection, there could be a phase shift or a path length difference. So it is the case that we get a phase shift if we're going from an index of refraction that's lower in value to the index of refraction it bounces off of. So in this case, since we're going from 1 to 1.33, there will be a lambda over 2 path length difference, or a pi phase shift. So that says that the phase shift between the incident beam and the reflected beam off the top is pi, or there's a path length difference of lambda over 2. Now, the beam went through and now bounces off the bottom part of the thin film, and again we're going from 1.3 to 1.5, so we're going to a larger index of refraction, and that means that at this point the reflection will pick up another phase shift of pi, or path length difference of lambda over 2, and then when the beam here refracts, there is never a phase shift picked up due to refraction, only due to reflection. So this beam then, that's going to be refracted from that one there, I didn't draw it very nicely, will still carry with it a lambda over 2 phase shift, which tells us that the total path length difference between the two reflected beams of the top and bottom of the thin film are actually interfering constructively. So we do see the reflection that comes from the top and bottom of the thin film. So now we want to know the three lowest thicknesses so we can see the light that's transmitted, that's reflected from the top and bottom, I mean. So the equation we have to then use is 2L is m lambda vacuum divided by the index of refraction in the thin film, and we want the three lowest thicknesses. So then we solve for L, and L will be m lambda vacuum divided by 2N2. So the lowest m's, if we plug in m equals 0, then we really don't get any thickness. So we want non-zero thicknesses. So the lowest one is going to be m equals 1, in which case L1 will be 1 times 520 nanometers divided by 2 times 1.33. And if we plug in the numbers for this, we get 195 nanometers. Then for m equals 2, the second lowest thickness will be 2 times 520 nanometers divided by 2 times 1.33. So that will be 391 nanometers. And the third lowest thickness is going to be for m equals 3. So L3 is 3 times 520 nanometers over 2 times 1.33. Plugging in the numbers, we get 586 nanometers. So here we have the 3 smallest thicknesses for which light reflected from the thin film will appear bright due to the reflection.